Hi everyone, welcome to the Digu Science channel. In this series, we will explore the relationship between self-inductance and induced EMF voltage. We're still using a solenoid. Consider this solenoid as part of an electrical circuit. Initially, the switch is open, and no current flows. This means there is no magnetic field. The magnetic flux is 0. Phi1 equals 0 Weber. Shortly after the switch is closed, current begins to flow. This current produces a magnetic field. Let's assume the magnitude of the magnetic field is B. Because the magnetic field penetrates the circular cross-sectional area of the solenoid has magnetic flux. N phi2 equals Li. The magnetic flux value changes from 0 to non-zero. A change in magnetic flux occurs in the solenoid. According to Faraday's law, a change in magnetic flux produces an induced EMF voltage. Let's write Faraday's law. Epsilon is equal to minus n d phi dt. The value of n is constant. This value can be shifted to the derivative calculation. The value of n phi is simply Li. In the same solenoid, the self-inductance L remains constant. We can exclude this value from the d/dt calculation. This is the formula for the induced EMF with respect to self-inductance, epsilon equals minus L di dt. This induced EMF is a quantity that has both positive and negative signs. Now, assume an electric current flows from left to right. When the current increases, such as immediately after we close a switch, the value of di dt is, of course, positive. We have studied derivatives in the previous semester. Determining the sign of the derivative is not complicated. We can ignore the sign of L, because the sign of this quantity is always positive. A negative value multiplied by a positive value will produce a negative value. From Lenz's law analysis, the direction of the induced magnetic field is to the left. To produce such an induced magnetic field, the induced electric current must flow from right to left. The direction of the induced current is opposite to that of conventional current. When the current decreases, such as when we open a switch, the value of di dt is naturally negative. A negative multiplied by a negative results in a positive value. From Lenz's law, the direction of the induced magnetic field is to the right. To produce such an induced magnetic field, the induced electric current must flow from left to right. The direction of the induced current is parallel to the direction of the conventional current. It seems easier to determine the induced current using the concept of self-inductance. When the magnitude of the conventional electric current increases, the direction of the induced current is opposite to the conventional current. Conversely, when the conventional electric current decreases, the direction of the induced current is parallel to the conventional current. Hopefully, this tutorial has provided an overview of Faraday's law and self-inductance. And don't forget to watch the next video.